We were talking about the general properties of the natural exponential function y equals e to the x, and we were down to talking about the tangent line through this point that is the y-intercept on this parent function. So here's the tangent line, and it turns out the slope of the tangent line through the point 0, 1 is 1. In other words, for the function f of x equals e to the x, the derivative of that function at x equals 0 equals 1. And the beauty part is that no matter where we are on this function, for instance, here is the point 1e, that when we take the slope of the tangent line through the point 1e, or f prime of where x equals 1, the slope is e there through that function, the slope of that tangent line there. And it turns out that the slope of the tangent line anywhere on the curve y equals e to the x is always equal to the y-coordinate of that point everywhere, from negative infinity to positive infinity. And this is a really great attribute to the function y equals e to the x, because what it means in practicality is that this function is its own derivative. The derivative of e to the x is e to the x. That's sweet. If we have y equals e to the x, then y prime is e to the x. Y double prime is e to the x. This function is its own derivative at any input value. Now, this is the form that I want you to actually put in your notes, because here's the form for the derivative of the natural exponential function using the chain rule. This says the derivative with respect to x of e to the u. Now, understand something. E is the outside. That's the outside. And we have fed inside some function in x. So when we verbalize the derivative of e to the u, we're going to see that we can use the same verbalization we always have. It is the derivative of the outside, and that's e. So there's the derivative of the outside, not changing the inside. That's why we just copy down u. Here's the inside, the derivative of the outside, not changing the inside, times the derivative of what's inside. Pretty handy. It's awesome, as a matter of fact. So that's the same verbalization that we used for any chain rule problem. Here is what's inside, and if it's an expression in x, then times the derivative of the expression u with respect to x. So the same verbalization that we've always used for our polynomials, our power terms, our trig terms, any kind of chain rule that we've needed still works for the natural exponential function. So make sure that this is what's in your notes. All right? Let's work a couple of examples so you can kind of see this in action. I realize that this is the lesson for the natural logarithmic function, but I always introduce the derivative of the natural exponential function here because we use it to develop the derivative of the natural log function. But I'm going to kind of, on a side note here, work a couple of examples using the derivative of e to the x so that you'll get a feel for how that looks. So when we get down to the lesson, that is the lesson over the natural exponential function, that lesson should go very quickly. All right, so here's our first example. The tangent to the curve. Tangent, when we read tangent, we think derivative. The tangent to the curve, y equals 2x times e to the negative x, is horizontal when x equals what? So this is a way of saying the derivative equals 0, right? The tangent to the curve is horizontal. So turning that into mathematics, that says the derivative equals 0. So let's find the derivative. Let's find y prime. Now y is a product. It's 2x times e to the negative x. Here is u. We have fed negative x into the e function. Here's the outside, here's the inside. So, product rule, 1 d2. It is the derivative of the outside, not changing the inside, times the derivative of what's inside with respect to x. So there's the chain rule for e to the negative x. So there's 1 d2 plus 2 d1. So there's y prime. Y prime equals negative 2x times e to the negative x plus 2 times e to the negative x. Now I want to know where that equals 0. For what x value does that equal 0? Well, we have a common term that we need to factor out. So let's factor out e to the negative x. That leaves us negative 2x in this first term, plus that leaves us 2 in this second term. So there is a product. So the only way that this product can equal 0 is for either this factor to equal 0 or this factor to equal 0. Now they both could equal 0, but usually we set every factor equal to 0 and find the x value where that's true. Well, this isn't the parent function e to the x. This is e to the negative x, which is equivalent to 1 over e to the x. Well, this will never equal 0. This factor cannot contribute at all to this product equaling 0. This factor is not playing a role as to where this product equals 0. Why? Because e to the x never equals 0, and 1 divided by any real number can never equal 0. So this is the only factor that's contributing to where y prime equals 0. So that is negative 2x equals negative 2, so x equals 1. And that is choice B. So there's your first derivative of e to the x example using the chain rule. Now, here is a free response problem. So a particle moves along the x-axis in such a way that at any time t greater than 0, so positive inputs only, its position coordinate is x equals sine of e to the t. So this function e to the t has been fed into the sine function machine, and this is the position function. So part A says find the velocity and the acceleration at any time t. So velocity, remember, is the derivative of position. So we're going to take the derivative of this function. This is a chain rule. It is the derivative of the outside, not changing the inside, times the derivative of what's inside. Remember, the derivative of e to the t is e to the t. So there's your velocity function. We could clean it up a little bit. This is e to the t times the cosine of e to the t. Remember, this e to the t and this e to the t, we cannot gather those terms. This e to the t has been put into the cosine function. This is the angle measure for cosine. This is just times e to the t. So this is a product. There's 1, there's 2. All right, so we also want to find the acceleration, which is the derivative of velocity. So this is a product. It's 1 d2, chain rule, derivative of the outside, not changing the inside, times the derivative of what's inside. So there's 1 d2 plus 2 d1. So there is the acceleration for the particle at any time t. All right, let's look at part B. I'll move this down a little bit. At what time does the particle first have 0 velocity. I want the first t where velocity was 0. So I'm going to come back up to my velocity function, and I'm going to set it equal to 0. E to the t times the cosine of e to the t needs to equal 0. Remember, we have a product. There's a factor, there's a factor. So it happens when e to the t equals 0, or it happens when the cosine of e to the t equals 0. Remember, what do we know about this? We know e to the t will never equal 0. And you know what? Show the AP reader that you know that. Write this down and show the AP reader that you recognize this factor has no bearing on where this product equals 0. Now, the cosine function will equal 0 the first time. I want the first t. When its angle measure, right here, there's the angle input. When that angle equals pi over 2, that's the first time cosine equals 0. So I'm going to take this angle measure, e to the t, and I'm going to set it equal to pi over 2, and then I'm going to solve for t. Well, how do I undo e to the t? I have to introduce natural log to both sides. I have to bring in the inverse function. So here, t, because that's what this cleans up to on the left, equals the natural log of pi over 2. So there's the answer to part B. Part C says, what is the acceleration of the particle at the time determined in part B? So now I have to go back up and pick up the acceleration function, and we might clean it up a little bit. Here's work for part C. We have e to the t times negative sine of e to the t times e to the t. So I'm going to put these e to the t's together. Notice that e to the t times e to the t, we use that exponential property that says when we multiply the same bases, we add the exponent. So this becomes e to the 2t. So that first factor, that first term is e to the 2t. I'm going to factor my negative, put this negative out front, times the sine of e to the t. And then I have plus e to the t, this factor, times the cosine of e to the t. So there I've cleaned it up a little bit, something I wouldn't have to do if I wasn't going to pick it up and do something with it. But since I'm going to plug values into it, I want to go ahead and clean it up a little bit. Now here's where these properties of the natural logarithm are going to come into play for us. We have e to the natural log of pi over 2. Everywhere there's a t, I'm just plugging in the natural log of pi over 2. That's all I'm doing here. Cosine of e to the natural log of pi over 2. All right, so let's clean this up a little more. Here's where we have that property that the natural log says that I can pop that power up front and make it the exponent of that term right there. So this is actually e to the natural log of the quantity pi over 2 squared. This, e and natural log undo each other, so this is just actually the sine of pi over 2 plus e and natural log undo each other, so that's actually just pi over 2, times the cosine, again, they undo each other, the cosine of pi over 2. Notice that I couldn't just have these two undo each other. It's not e to the 2 times natural log that undoes each other. It's e and natural log. So this actually cleans up to pi squared over 4 times the sine of pi over 2, which is 1. And you know what? I dropped my negative, so we better be careful on that. And plus pi over 2, and the cosine of pi over 2 is 0. So the acceleration at the time determined in part B is negative pi squared over 4. So I'm going to stop here. We'll go on to a third video and we'll pick up on our work of the natural log function.